You learned this in school. The area of a circle is πr². You've used it 100 times since. But have you ever actually seen why it's true? Not the formula, the reason behind it. This is Symmetry. Let's find out why. It starts with a problem that took humanity 2,000 years. Here's why the circle was so hard. Measuring the area of a square is easy. You tile it with smaller squares and count them. But a circle is bounded by a curve. Lay a grid over it, and the squares along the edge always spill past the boundary or fall short. No matter how small you make them, straight squares never perfectly fill a curved shape. Around 250 BC, Archimedes found a way in. Instead of fighting the curve, he trapped it. Draw one polygon inside the circle, touching it, and one polygon outside, wrapping it. The circle is caught between them. Now keep doubling the number of sides. 4, then 8, then 16, 32. And watch what happens. The more sides you add, the tighter both polygons hug the circle. Their areas close in from above and below, squeezing toward a single value. Archimedes called this the method of exhaustion. And hidden inside it is the one idea this entire video depends on. A curve can be approached, as closely as you like, by straight pieces. And Archimedes didn't stop at the idea. He pushed his polygons all the way to 96 sides, by hand, with no algebra and no decimals. From the inside polygon and the outside polygon, he proved that pi must lie between two fractions, 22/7 above and 223/71 below. In our decimals, that pins pi between 3.1408 and 3.1429, over 2,000 years. But before the area, we need to understand one number. Pi isn't a random symbol from a textbook. It's something you can measure with a piece of string. Take the diameter of any circle and lay it along the edge, end to end. It fits 3 times with a little left over. That little bit is about 0.14, so the circumference is roughly 3.14 diameters. That ratio is pi, and it's the same for every circle in the universe. Since the diameter is 2 radii, we can write the circumference as 2 pi r. Unroll the edge of the circle into a straight line, and that's its length. 2 pi r. Hold on to that number. In a moment, exactly half of it is going to matter. Now, the trick that finally cracks the area. Take the circle and cut it into thin wedges like slicing a pizza. Now pull the wedges apart and lay them in a row, one pointing up, the next pointing down so they interlock. With only a few slices, the top and bottom are jagged, but remember Archimedes. The more slices you use, the straighter those edges become. Push it far enough and the wavy shape settles into something you know by heart, a rectangle. And here's the beautiful part. We rearrange the pieces. So let's just read the rectangle. Look at its height. Each wedge reaches from the center of the circle to its edge. That's a radius. So the height of the rectangle is simply r. Now the base. It's built from the curved edges of the wedges. Half of them point up, half point down. So the base is made of exactly half the circumference. Half of 2 pi r is pi r. And the area of any rectangle is just base times height. So the area of the circle is pi r times r, which is pi r². There it is, the same formula you once memorized. Except now, you didn't memorize it. You watched it come from somewhere. But there's one honest question we skipped. With a handful of wedges, the shape isn't really a rectangle. The top is still bumpy. So is this proof just an approximation? Here is the magic. As the number of slices grows without limit, those bumps shrink toward nothing. The shape doesn't just look like a rectangle. It becomes one exactly. Almost turns into precisely. And that leap from almost to exactly is the same move Archimedes made with his polygons 2,000 years ago. It's called taking a limit. 19 centuries later, that exact idea grew into calculus, the mathematics of curves, motion, and change. The whole thing was hiding inside a sliced-up circle. A good result deserves a second proof. Forget the pizza slices. This time, picture the circle as a nest of thin rings, one inside the next, like the layers of an onion. Pick any single ring at some radius x. It's really just a very thin strip bent into a loop. Its length is its own circumference, 2 pi x, and its thickness is a tiny sliver, dx. Now unroll every ring into a straight strip. The outermost ring is the longest, 2πr. Each ring inside is a little shorter, all the way down to the center, where it shrinks to nothing. Stack those strips on top of each other, longest at the bottom, and they pile up into a right triangle. Its base is the longest strip, 2πr. Its height is the radius, r, and the area of a triangle is 1/2 base times height. 1/2 times 2πr times r. And this idea doesn't stop at flat shapes. Take the same spirit into 3 dimensions, and something lovely falls out. If you could peel the curved surface of a sphere and flatten it, it would cover exactly 4 circles of the same radius. Not 3, not 5, 4 precisely. So the surface area of a sphere is 4 times πr². The humble circle you just measured is hiding inside the sphere, the cone, and every round thing there is. That's the real reward here. Not one formula, but a way of seeing. Straighten the curve, and the mystery dissolves into arithmetic. It's the same move whether you're slicing a pizza, peeling an onion, or unwrapping a planet. So πr² was never a magic spell to memorize. It's a circle, straightened into a rectangle, read one side at a time. If that gave you a small jolt of, oh, that's why, then that's exactly what symmetry is for. Subscribe, and every week we'll make one more piece of math or science click. And if it did click, a like helps it find the next curious person.